Hello everybody and welcome back to Things You Should Remember from Strength and Materials, but have likely forgotten. This should be the final part of this series. I only plan on doing three, so let's get into it. Last time in our combined stresses video, we got down to these two elements, H and K. I'm going to stick with K for the rest of this example as we find our principal stresses and our max shear. If you want to use just the equations, here they are. Sigma 1, 1, sigma 2, 2 are the principal stresses for a 2D Mohr circle, and our shear max, well, is the shear max. And so filling in for the numbers, sigma x and sigma y are just our two observed stresses, normal stresses, on the element. So negative 506 and 0. 0 is still a valid stress, so we have to include it. And using our shear value of 233, we get our principal stresses of negative 596.9, that's compression, and plus 90.9, tension, and our shear max of 343.9, all of these in megapascals, of course. Well, if you're okay with where we are here, this is all you really need for Machine Design 1. We don't actually build more circles anymore, so you don't need to bring the visual along with the equations. However, if you do need the visual, let's continue. So we build our Mohr circle on a graph looking like this, where our horizontal axes are our normal stresses, tension on the right for positive, compression on the left for negative. And our shear, our tau, is on our vertical axis. Clockwise rotation on the top, counterclockwise rotation on the bottom. I don't know why we do it this way. The way I remember is that if we have a pinned connection at our center point, 0, 0, I know that the two axes will collapse down onto the positive one with their associated rotations. And so we begin with our first point. I'm going to use the top side of element K, and this is how we get our first point. We take our stress value, in this case 0, and I guess to help visually represent how we do this, I form a straight line. Somewhere on that line is our first point, and it'll be corresponding to either 233 up on the shear or 233 down. But how do we know? The way I explain it is we look at the shear arrow, just the one associated with that top side of our K element, and we observe what kind of rotation that arrow would bring to element K if it had a center point. In this case, our shear arrow brings a counterclockwise rotation, and so it goes on the counterclockwise axis, down to negative 233. Similarly, we look at our left side. We have our normal stress of 506 megapascals in compression, so it goes into our negative sigma, and 233 MPa for our shear. This one is causing a clockwise rotation, so it goes on the top side of our vertical axis. From here, we need to get our center point. Center point being the average between our 2 points. We know that the midpoint between 233 and negative 233 is 0, so we're right on our horizontal axis. And we find our stress average by taking our two normal stresses, negative 506 and 0, adding them together, divide by 2, we get negative 253. That is the center point of our Mohr circle. Our next step is to find the radius, and we kind of use Pythagoras, as I've shown here. Our horizontal, or our bottom part of our triangle is 253, and the vertical side is 233. We use Pythagoras, and we get a radius of 343.9. From here, we get our endpoints of our circle that fall on our horizontal axis. We take our center point, and we add our radius to get 90.9, the point furthest right. And we also take our center point, our average, negative 253, and we subtract 343.9 to get our leftmost point, 596.9. Now I've tidied it up a bit, but we get our Mohr circle here. We get sigma 1, 1 as our leftmost point, sigma 2, 2 as our rightmost point, and our shear max at the top. And these numbers do correspond with what we got from our equations. The numbers don't lie. So you can use a Moore circle if you need the visual aid, or you can use the equations if you're comfortable with it. Now I know in strength of materials we got into the angle of rotation of the element on Moore circle. We don't do that in Machine Design 1. I don't know about Machine Design 2, but this is kind of all you need. But in case you want to learn about the angles as well, I've done that for you. So the angle of rotation on Moore's circle we call 2 theta. It is the angle between this red line and our horizontal axis. To find 2 theta, we take that same triangle that we had before, the horizontal axis being 253, the vertical side being 233. We use tangent. We find 2 theta on our Moore circle is 42.64 degrees, and theta is 21.32 degrees. And so we have 2 theta on our Moore circle and theta on our element in the bottom right. Our element has to be rotated by half of what it is on Moore's circle. I'll get into that a little bit later. A question I often get is, how do we know which side is going to have which principal axis? How do we know that the top one is going to have 90.9 and the one on the left is going to have 596.9? I explain this with this kind of diagram. If we look at the point on the left, our original 506, 233, we have to rotate it down the amount of 2 theta to get down to negative 596.9. That's that same point. That is that same side of our element K on the top left. It is being rotated counterclockwise and has transformed. It has become, or how do I say this right? It now has a stress of negative 596.9 with no shear. And so that side on our left, on our original element K, is still the side on the left. It just now has a stress of 596.9 going up and to the right at 21.32. Similarly, if we look at our original point 0 and negative 233, it goes counterclockwise 42 degrees up to the horizontal axis to become 90.9, and we reflect that on our newly rotated element as well. Another question I get is, why is it 2 theta on Moore circle but only theta on our element? That's a good question, and I use this diagram to help explain that. If we look at the element as shown in the top right, or sorry, top left, I have the blue line on the top, red line on the side, and we're going to focus on that blue line first, the 0, negative 233. That's already been labeled on our Moore circle. And so if we rotate that counterclockwise by 90 degrees, we get our diagram on the bottom left, where our blue line is now on the left side and our red line is now at the bottom. We move the element, the stresses don't change. What do I mean by that? I mean our horizontal normal force is always going to be 506 no matter what side it's pushing on, as long as it's still in the horizontal axis. If we pick up our element, rotate it 90 degrees and put it back, we now have 506 megapascals of compression now pushing on the blue side. So if we go back to our Moore circle and we rotate counterclockwise 90 degrees like we've done in our element, we get to that point up top right with those 3 question marks. I don't know what it is, but I know it doesn't correspond to what's happening to that blue side anymore. What's happening on that blue side is 506 megapascals of compression with a clockwise rotation of 233 from our shear. That is absolutely not that point with the 3 question marks. If we go a further 90 degrees counterclockwise on our Moore circle, we finally get to the point that corresponds with what's happening to that blue side in the bottom left element. 506 megapascals in compression and 233 megapascals in shear. That is how I explain why it's 2 theta. It's a whole 180 degrees from our original point of 0, negative 233 to get to our 506, 233. It takes a 180 degree rotation on our Moore circle to line up with what's happening after we turn our element 90 degrees. That's how I explain it. It's not the best explanation, but in the end you don't need this for Machine Design 1. And yeah, we've come to the end of the series. Yeah, if you have any questions, please feel free to leave a comment. I'll do my best to answer them through text. And good luck in your semester this year.